So that concludes the discussion on generating functions in this context, and we are going to move on to the next technique in our arsenal for this week. And before we do that, we have to remember symmetry groups that we discussed when we defined algebraic structures and especially groups. Recall that the structure G with an operation star is called a group if the operation, well, star here is a binary operator, which by definition means is closed on set G, and the operation is associative, and it has an identity element. The, the set with respect to this operation has an identity element, and all elements have inverses. So this was the definition of a group. And we will also denote the order of the group, which is equal to the cardinality of set G. And next definition is the symmetry group, which we actually gave an example when we discussed groups. But maybe if you don't remember it in detail, what a symmetry group is the following. Let this S sub A be the set of permutations on some set A. Now remember, a permutation is a bijection from a set to itself. Okay, so it's just a reordering of the elements in the set. So S sub A is defined as the set of all possible permutations on this set. The structure, the algebraic structure S sub A, so this, the set of permutations, with the operation of function composition, okay, is called the symmetry group of A. Okay, so you have a finite set A, and the set of all possible permutations that you can define on A, along with function composition, forms a group, and this we call a symmetry group. Now, if you remember, permutations can have what we call the quotient notation, where, for instance, the element 1 is mapped to 4, element 2 is mapped to 1, 3 is mapped to itself, and 4 is mapped to 2. So here, actually, sigma 1 equals 4, sigma 2 equals 1, sigma 3 equals 3, and sigma 4 equals 2. This is one way to represent a permutation, but there is another way to represent a permutation, which we call the cycle notation. If you look at this quotient notation, 1 goes to 4, and then 4 goes to 2, and 2 goes to 1, and the cycle is complete. So 1 to 4 to 2, 1 to 4 to 2 is one cycle, and 3 by itself forms a single cycle. So with parentheses, we actually separate the cycle, and the order of the elements here is significant because it means 1 goes to 4, 4 goes to 2, and 2 comes back to 1. Okay? But the order of the cycles is not important, so you can write 3 first. And indeed, the order of this is important, but you can actually rotate them because 1 goes to 4, 4 goes to 2, 2 goes to 1, but also 4 goes to 2, 2 goes to 1, 1 4 goes to 4 describes the exact same cycle. So that's another way of representing this. Sometimes the single cycles, like 3 going to itself, might be dropped. So this is an alternative way of representing permutations using the cycle notation. And a k cycle is simply a cycle of length k. It's a sequence x1, x2 up to xk of elements from set A that satisfies this. It's simply this is mapped to x2, x2 is mapped to x3, x3 is mapped to x4, etc. And then finally xk is mapped to x1. This is simply the definition of a k cycle. Now, this is the structure we call the symmetry group. Using these definitions, we are going to describe Burnside's lemma. Now we have a G, a group with identity element E, and A is a set. Now G is a group of permutations, so G has functions as its elements, and A is a set where the permutations are defined on. So we are going to define a function alpha from the Cartesian product of G and A to A, right? So what is this? Alpha accepts as input ordered pairs where the first element comes from G. So the first element is going to be a function because this is the group involving permutations. So let's say sigma, or let's say sigma 1 indeed. Okay, and the second element is going to come from A. Let's call that x1, and this is mapped to an element in A, let's say x2. Okay, so this is a function which takes its input as its input a permutation and an element, and it gives a second element. Okay, so a function alpha defined in this way, where you apply G, a permutation, to an element and to write Gx. This is in fact just the application. This is called a group action if the following holds. You have the identity property where for any element x in the set A, Ex equals x. Remember what E is. G is a group with identity E. So essentially, this is the identity permutation, which is simply mapping all elements to themselves. Okay? And secondly, you have compatibility, which means for all elements X in set A, and for all permutations coming from set G, G and H, this equals this. So what are these? Okay, so H applied to X, and whatever is the outcome, you apply G to that, or you compose G and H, and then apply it to the element X. So these should be equal, and we call this property compatibility. Okay, and this, if these two are satisfied, we say that this function alpha is a group action. And if this is the case, we say that group G is set to act on set A. So this is a little bit confusing, probably, maybe due to the notation, but it's simply we have a set of permutations along with function composition that forms a symmetry group, and you have the set that the permutations are defined on, and the group action is simply applying a permutation on one of the elements. That's simply what this definition tells us.